Hello everyone, this is Mustafa here, solving soil mechanics problems for civil engineering students. In this video, I'm talking consolidation, and this is question 11, and you can refer to my other videos for more problems. We have an interesting problem here. Let us see what we've got. So we are given here a soil profile of clay. You can see here that is soft clay, 5 meters thick, and also given consolidation test results for the clay in terms of the water content coefficient or the compression index, the recompression index, CV, etc. And we are told that the water level drops by 10 meter below the clay top surface. So this is the clay top surface here, which is 20 meter below the ground surface. And the water level will drop here by 10 meter below the clay top surface. So if the clay thickness is 5 meters, it means that the water will go deep below the bottom surface of the clay. So what's required? Required is to determine the settlement of the clay due to the water drawdown. You should know that if the water level drops for any reason, there will be a subsequent increase in the effective stress within the soil that experience this drop in the water level. We are also required to determine the heave of the clay subsequent to its settlement due to water returning to its original level. So we are told that after the water drop by 10 meters, settlement will happen, determine this settlement, and then when the water level rises again, determine the heave or the swelling, if you like. Solution strategy for problems of that nature. First, we need to determine the in situ stress, that sigma dash V naught, at the strategic locations. The clay thickness here is 5 meter, so it's handy to divide it into several layers. So first is to determine this sigma dash V naught, and then determine the stress increase within each layer or sublayer due to the drawdown. After that, we can calculate the settlement and the heave as needed. So what is the essential knowledge to solve that problem? First, we need to determine the in situ stresses due to water level variation. As the water goes up or the water goes down, we need to perfect how we can determine the impact of this on the in situ stresses, and then apply the settlement and the heave, which you can call it also swelling equations. So let us solve these problems. So here, first I have a soil, thickness H, and we need to determine whether this soil is normally consolidated or over consolidated. If the soil is normally consolidated, so on that plot here, void ratio versus log stress, it means that the compression state of the sample or of the layer will actually move down this curve. So the direction here is only down this curve. If the soil, for whatever reason, is over consolidated, like removing the stress from this point here, so there will be a swelling curve. You can call it unloading, reloading. This is why we have these two arrows here. And any subsequent swelling will be along that line in that direction. Or if you have recompression, it will be downward still along that direction. The settlement equation that governs settlement along the normal compression line is that one. On the other hand, if we are experiencing settlement or swelling, it's going to be along that CR or the recompression index, and this is a governing equation. Now, this is the problem. This is a 5 meters clay, and now we need to calculate the initial stresses within the clay first. We said that the clay thickness is 5 meters, so it's a good idea to divide the clay into sublayers. So I have here 1, 2, 3, 4, 5 sublayers, and I have marked here 5 points within the middle of each of these sublayers. Point A, B, C, D, and E. So point A is in the middle of the top sublayer, so it's 0.5 meter from the clay top surface. B will be 1.5 meter, C 2.5 meters, and so on. So let us determine the unit weight of the clay. Why? Because we are not given the unit weight of the clay. What we are given here is the water content of the clay. Remember, this clay is saturated. So the equation is void ratio times the degree of saturation equals water content times specific gravity. That's a very critical uh, formula that you need to know. And underwater, so the degree of saturation equals 1. Assume GS equals 2.7. If it is given you to you, that you just use it. So we substitute here. So E is the water content. That's 55%, 0.55 times the specific gravity, 2.7. So I have 1.485 for the void ratio. I can apply this formula here. It should be given, or if you memorize it. So gamma saturated is specific gravity plus E divided by 1 plus E gamma water for a saturated material. We'll plug in these values here. So GS is 2.7, void ratio 1.485 divided by 1 plus E times gamma water 9.8. So I got the saturated unit weight of the clay, 16.81 kilonewton per meter cube. This will enable me now to determine the in situ stresses at each of these points within each sublayer. Let us take point A. So point A, remember, this clay has 20 meters of some sort of sand gravel material on top of it. So I have 20 times 17, that's 20. That is the thickness of this overburden above the clay. 17 is the saturated unit weight here. So it's all saturated. 17 plus zero point 0.5, because this is the thickness of the clay to point A, times 16.81 minus 9.8. 16.81 is a saturated unit weight, so it's submerged 9.8. Note here that I did not consider this layer to be submerged, so I considered the water surface to be initially here at the top of the clay. So this is why I used the full 17 kilonewton per meter cube. If the water was here at the top, so you would use the buoyant unit weight for that. That's very critical. So now I determined the in situ stress at point A that represent the first sublayer of thickness 1 meter. We can repeat this for point B, C, D, and E. It's exactly the same process. As you can see here, each time I'm just adding the submerged weight of the clay. Let's take point E. So point E, it's 4.5 meter from the clay. So it's carrying 20 times 17, that's 20 times 17, plus it's carrying 4.5 meter of buoyant clay. This is why I take away here the unit weight of the water. So I ended up with the overburden pressure effective at point E, and I have the values for the various layers. So this is the initial before anything happens to the water level. Now we need to calculate the stress increase due to drawdown. So the water level was here, coincident here with the top surface of the clay, and then dropped by 10 meters. So it became somewhere here, meaning leaving the clay saturated, not submerged. There are two methods to do that. First, there is a rule that you need to know. Every 1 meter drop in water level increases the effective stress by a magnitude equivalent to 1 meter of water pressure. So 1 meter of water pressure is 1 meter times the unit weight of the water, that's 9.8. So if the water level drop by 1 meter, it means that the soil within this 1 meter will experience increase in effective stress. Its magnitude is 1 times 9.8 equals 9.8 kilopascal. Or you can work out the overburden pressure again, but now considering the clay to be saturated but not submerged. And the difference would give you the increase in the effective stress due to the drawdown. If you are happy to use this one, it's gonna be very fast. Let us see how this will unfold. Okay, so let us apply method 1. Delta sigma dash V equals H water times 9.8 as we just explained. So we will apply this to every point here. Point A, point A, it is seeing that the water level dropped by half a meter because the water was here, okay, that was half meter above point A and then it disappeared. It means that the water drop is zero point 0.5 meter. You multiplied by 9.8, so 4.9. So point A experience increase in the effective stress, its magnitude is 4.9. When you add it to the overburden pressure that we just calculated before, so it was 343.5, so it's gonna give you 348.4. You repeat it again for point B. So point B saw the water level in the beginning at that level and then it disappeared. So it lost 1.5 meter of water. So this will be reflected as overburden pressure onto point B. So it's 1.5 times 9.8, 14.7. Again, you add it to the existing in situ stress. And so on for the rest of the point. This is point E here, not point G. So for point E here, let us see this. So point E used to see 4.5 meter of water above it. Now the water disappeared, so the stress increase will be what this point has lost, 4.5 meter of water multiplied by 9.8, and this is the corresponding overburden pressure after we added the change in effective stress. Method 2, like I said, all we need to do is to calculate the overburden pressure again at each point. So point A, like last time, it is seeing 20 times 17, plus it is seeing 0.5 meter of saturated clay, but not buoyant, remember, here. So 16.81, it's 348.4, exactly like with what we got before. And then we repeat it for all other points. Point E is seeing 20 times 17, plus it is seeing 4.5 meter here, 4.5 meter of clay that is saturated but not buoyant. The reason is that the water level dropped below the clay. So I ended up with 415.6. So now I have everything. I have the in situ stresses. I have also the change in the effective stresses. So I can basically just substitute here in this equation. So I will show you the table and then we check each point here. Remember, I have 5 sublayers, 1, 2, 3, 4, 5. So layer 1, 2, 3, 4, 5. And the thickness of each sublayer is 1 meter. 1, 2, 3, 4, 5. And this is the settlement equation. At point A, we substitute in that equation here. So CC over 1 plus E naught, CC is given as 0.4. E naught, we calculated it, if you remember, from the water content. Substitute here, so CC over 1 plus E naught is 0.161. And it is the same for all sublayers because the clay is given as uniform. So for sublayer 1, you substitute here, CC over 1 plus E naught is 0.161, that's 0.161. H is the thickness of the compressible layer, it's 1 meter. Log sigma dash V naught for this clay, for this sublayer is 343.5. This is the effective overburden pressure before anything happened to the water. Plus the change in the effective stress is 4.9 due to the water level dropping by 0.5 meter from above point A divided by 343. This is 343.5, not 348.4, 343.5 here. And this has given me 0.001 meter. So you repeat it for everything else, and then you do the summation here. So the settlement is 23 millimeter due to drop of the water level below the clay. It wouldn't make much difference whether the clay or the water level dropped by 10 meter or 8 meter or 20 meter, as long as it has left this clay entirely. So now we are required to calculate the heave due to rise of the water level. When the water level rises, the effective stress in the clay will reduce and the clay will swell. We said this before. But now when it swells, it will not swell along the virgin compression line, the blue one that I showed you before, but it will swell along the red line. So to determine the heave, we will need to apply this formula here using the recompression index CR instead of CC. So let us see how we will do that. Okay, here we go. So this is the virgin compression curve. From this point here, the water started to increase again, so the clay will swell along that line here, which is the red one. So we will now substitute in this equation. Here, H here is for heave, but we will need to determine the void ratio after settlement because we need the void ratio here. So after settlement, the governing equation, you need to know this by heart, that change in the thickness divided by the thickness equals the change in the void ratio divided by 1 plus E naught. Well, to be honest, the impact of using the updated void ratio may not be that significant. We'll see in a minute. So delta E is 0.023. This is the compression happened to the clay due to drop of the water level divided by 1.485 times 5, which is the overall thickness of the clay. So what we are saying here, that the clay on average, its void ratio will drop by 0.046. So this means that the void ratio at this point will be 1.439. And this what we'll be using to calculate the heave. So the heave, exactly like the other equation, CR over 1 plus E dash now. So 0.05, that is the recompression index given. 1.439 is the void ratio we calculated. And here we substitute. So 0.0205 is this formula times H, which is 1 meter because we are doing this for a sublayer, and this is 343.5 like we said before. So this will give us 0.001. We repeat this for all other layers like before, end up with 3 millimeter for each of these sublayers. This should be straightforward for each layer. Again, sigma dash V naught, delta sigma dash V naught. Just to remember now, rather than we are compressing along that line, we are swelling along that red line. But the stresses are exactly the same. So sign-wise, it's a negative versus positive or vice versa. So let us compare. The settlement due to heave is 0.003. Settlement due to compression because of the drop in the water level is 0.023. So the ratio is very small, 0.127 here. Let us compare this with the ratio of the recompression index and the compression index, because it looks that the ratio will be more or less the same. Let us see. So recompression index 0.05, the compression index C sub C is 0.4, it's 0.125. These are almost the same. So we could have said directly that the ratio of the settlement to heave or heave to settlement will basically be the recompression index divided by the compression index, because we have a condition here, that is the change in the stress is exactly the same. This doesn't apply if the swelling happens over a stress increment that's different from the same stress increment that caused settlement in the first place. So hopefully you enjoyed this problem, and I will see you in more videos.